In the last part of this module on power measurement, we illustrated how one can measure the power usage of an element using a combination of readings from a voltmeter placed in parallel and an ammeter placed in series. We noted to make a current measurement, the circuit needs to be broken and the meter needs to be placed in line, as we see in this example. This is problematic if you are attempting to make spot readings of equipment, appliances, etc. that are already in service. As an alternative, we present a technique for determining power draw in AC systems that gets around this practical constraint. Power systems in the U.S. are based on 120 volts RMS 60 Hz signal that is delivered to your home. Recall that RMS refers to root mean square, or as illustrated in the equation below, is the square of our sinusoidal signal averaged over time and then square rooted. For sinusoids, the RMS value is simply the magnitude, in our case 170 volts, divided by the square root of 2, or 120 volts RMS. Our use of AC power is a result of our desire to transmit power over very long distances. Conductors used in power lines are not ideal, and thus incur power losses that are proportional to resistance and current square as seen in this equation. Now, resistance is dependent on multiple parameters, some of which we have control over and others we really don't. For example, the line length is dependent on where we want to run our service, and we can see the resistance is proportional to that. Now, sigma is the conductivity, and that's dependent on the material that we're using for the conductor. For example, copper is preferred over other materials due to its higher conductivity than, for example, aluminum. A, in the denominator, is the cross-sectional area of the wire, so cables that pass higher currents tend to be larger in size to reduce this I squared R losses. Wire is specified according to its gauge, for example, using the American Wire Gauge, or the AWG acronym, as you might have seen. Now non-intuitively, lower gauge wires are larger in cross-sectional area, and thus are designated for higher currents. Now, there's a practical limit on what we might choose for wire materials and its size, and so there's only so much we can do to make line resistance small. As such, the only other way to reduce line losses is to reduce the current flowing in the conductor. To do this, we take advantage of the AC properties of transformers. You probably recognize the devices in these images as the transformers you see in your neighborhood. Their purpose is to convert, that is transform, the AC voltages from one level to the next. For example, this pole-mounted transformer converts a high voltage to a lower 240 volts that goes to your house. So how does this reduce line losses? To answer this question, let's take a high-level look at what a transformer does. Fundamentally, a transformer couples two AC circuits using a pair of magnetically coupled windings, as we see here. An ideal transformer will have the same power coming out of the secondary as enters the primary. That being said, the voltage at the secondary depends not only the voltage at the primary, but also the number of turns in the primary relative to the number of turns in the secondary. For example, in this figure, we see there are less turns in the secondary than there are in the primary. As a result, the voltage at the secondary will be n times, where n is the turn ratio, and in this case less than 1, the voltage at the primary. However, as power is constant, this implies that the current provided at the secondary must be greater than the current at the primary by a factor of 1 over n. In short, for this example, the primary voltage is greater than the secondary voltage, but the secondary's current is greater than the primary's current in order to have power equivalent on both sides of the transformer. The previous example was that of a step-down transformer, as the voltage was lower at the secondary than at the primary. However, to reduce the current flowing in a transmission line, we use a step-up transformer. To convert the power signal coming from the power station to a very high, relatively low current signal. Once at the distribution point, that is, your neighborhood, This signal is retransformed using a step-down transformer to a lower voltage, higher current signal for use in the home. This strategy reduces the I²R losses that occur in the transmission line. Another type of transformer is the split-core transformer, which only has a single coil. A split-core transformer is useful as a current clamp, which is the device that allows you to measure current in a line without putting an ammeter in series. We clamp the split core about the line of interest, and the field that's created by the line when current flows through it becomes coupled to the coiled windings, thereby inducing a current in the coil. This coil current, when passed through a small resistance, produces a measurable voltage that is proportional to the line current of interest. For AC power systems in the US, we know the RMS voltage is going to be between 110 and 120 volts RMS, and thus by knowing the line current, we can ascertain the power being drawn by whatever device is connected to the line. Here we show an example of a current sensor in use. The split-core current sensor is clamped about only one conductor of a power cord going to the device being measured, in this case a 100-watt light bulb. So we see one conductor is being clamped and the second conductor is outside the current clamp. The current drops 4.6 millivolts across a 10 ohm resistor, indicating that the coil current is 0.46 milliamps. The sensor has 2,000 turns, which implies the line current is 0.92 amps due to the 2000-to-1 ratio. If 110 volts RMS is at your outlet, then by V times I, we have a power draw of 101 watts. In the lab, complementing this module, you'll build and calibrate your own split-core current sensor.